Hello everyone, this is video 15.3. We're going to be looking at centers of data, mean, median, and mode. And we'll talk a little bit more about what we mean by center of data and what we mean by mean, median, and mode and how to calculate those over the course of the video. So hopefully you've watched the previous videos and you have a little bit better understanding of what we mean by data, and you've looked at some types of graphs and you've seen that the graphs sort of have different shapes to them. And so now we're going to start to look at how we can quantify or put like a number to some of the aspects of those shapes. So this video 15.3 and 15.4, we're going to be looking at ways to use numbers to describe the shapes of some of those graphs. So let's get started. So we should define what we mean by a measure of center. And what we mean by that is a number that will describe the quote unquote center of the data set, which is almost exactly what the thing says. So you may have noticed in some of the previous graphs that we looked at in the previous videos that you might have something like this. And so here's your x-axis, and that's kind of curving up more than I want it to, but we'll fix that. We'll make it kind of curve down like that. There we go. So where is the center of this data? So there's a couple different ways we can think about what we mean by center. So one way we might think of would be the tallest point. And one place might be to take this and figure out where the middle of that would be. And then one place might be where it would balance. So if you look at this part here, this part is going to be a little bit heavier because there's more of it. And down here, so down here is going to be a little bit lighter, and so we'll hear because there's less of it. So we could think about this graph like if it was cut out of wood, and we wanted to put something to sort of like balance where that might be. So it might balance somewhere like here. So you can see that depending on how we think about the center, we could have multiple ways of figuring out what that is. And those three ways are going to be sort of what we're going to be talking about in this video: the mean, the median, and the mode. And we'll talk about how these three things that I've just talked about sort of relate to those ideas of the mean, median, and mode. But this is what we mean by the measure of center. And one of the important things I want you to take away from this is that there's more than one way to think about the center of a data set. So the first way we're going to look at is what is referred to in the book as the mean, which is more specifically the arithmetic mean. There are other types of means. We're not going to get into those in this class, but just sort of know that there are other means. And so when someone says arithmetic mean, they're not being picky necessarily. They're just being specific. So the arithmetic mean. This is also sometimes called the average, and average is kind of a bad name for it because it's a very generic way of putting it. So when someone says average, they probably mean the arithmetic mean, but it's probably not the worst thing just to clarify and do so in a way just to make sure that we're talking about the arithmetic mean, right? Or we're talking about the mean. There's some vagueness in the language when we talk about mean and average, but for the most part, in this class, we say mean or average, we're talking about this arithmetic mean. This is the average that you probably know how to do, where you add up everything that you have and then divide by how many numbers are in the set. So if we wanted to find the mean of 1, 4, 5, 5, 7, 8, 11, 11, 11, we would just add all these up. So 1 plus 4 is 5, 5 plus 5 is 10, 10 plus 5 is 15, 15 and 7 makes 21. What? 22. Mistakes happen. 22. And then 8 and 22 make 30. This is all makes 33. So we have 63 as our sum. And now if we want to count how many things are in the data set, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9. So my mean is going to be my sum over the size. And so I've got 63 over 9 equals 7. So the mean of this data set would be 7. Now, one way to think about this 7 is that it is the balance point. So this is what we were kind of talking about earlier in that picture that I drew about one way of thinking about the center. So this is the previous data set shown as a dot plot. So we've got little dots here to represent each of these. If we think about the number line, like being say a yardstick, and each of these numbers being like a little block of wood, so and they all weigh the same. If I put one here and I put one here and I put one here and here and I put these blocks where these numbers are, I could put something underneath the 7 and it would balance that little triangle, like a little balance. And so we can see how this works because if I look at how far everything is from the 7, so this is a distance of 1. These are all a distance of 4. So this gives me 13 to the right. So my numbers are 13 to the right. If I look at these two, these are 4 away total, so 2 each, so 4. This is 3 away, and this is 6 away. And so if I add these up, 6 and 3 is 9 plus 4 makes 13 in this direction. So I have 13 units away to the right, 13 units away to the left. That's going to make it balance. And you could see that if I were to take this block, where's my pointer? If I were to take this block here and move it over here, well, now it wouldn't balance anymore. Now I would have 14 on the left and 13 to the right, and now it would start to tip the other way. As I start to move these blocks around, then the balance point starts to change, which should convince you that if I were to change that 5 to a 4, that the mean would now start to decrease. It would become a little bit less than 7. So this is a really good demonstration that you can do with students to sort of show what the mean is as a balance point. It's a very kinesthetic activity way of seeing like literally how these things will balance out and balance this data set as a physical model. Another way we can think about this is this idea of leveling out. And so if I were to take the data set, so I've got 1, 4, 5, 5, 7, 8, 11, 11, 11. So if I were to put these as little blocks, so 1, 4, 5, I didn't have a nice little picture prepared for this one, 5, 7, so that's 5, 6, 7, 1, 2, 3, 4, 5, 6, 7, 8, and now I've got some 11s. So 1, 2, 6, 7, 8, 9, 10, 11, and then the same thing here, 2, 3, all right. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There we go. Sorry about that. So I want to balance these out. So another way of thinking about balance is maybe not necessarily that these are equally weighted on a number line, but that I have a uniform height. So I could take, and I'm going to go to red here, I could take these 3 and cancel them out and move them here. So now I've made these a little bit shorter and I made this a little bit taller. And I could take these 2 and move them here. So now they're the same height as these 5. And I could take these 4 and move them here. 1, 2, 3, 4. And so now these are all the same height. And I could take these 4 and move them over here. 1, 2, 3, 4. And now notice when I do that, these are all the same height now. These are all the same height. I've taken these blocks from over here and moved them over here to where now it's balanced as far as the height goes instead of as distances go. So now how tall are all of these stacks? They happen to be 7. Now, This example I chose because it works out to a nice even number. If the mean was 7.5, then it's going to be hard to get 7.5 x's in each column. That's not going to work out as well. So this is going to work out specifically to this example. But you can see that if you want to use this model with a class to pick an example where the mean turns out to be an integer, turns out to be a whole number, and then this model makes sense. This model is a lot easier to show. So the balanced one gives us a little bit more flexibility, but I think that this model uh, works equally as well in a different way, even though it's a little bit more limited as to when you can use it. But these all show what the mean is, and it's really important that students and you understand what mean is as something other than just a process. That okay, well now you know to add the numbers and divide by how many you have, but what does it do? Like what does it look like? How does it act? Having some sort of concept for what the mean is and does is going to be more important than just being able to calculate it. So the other two, median and mode, we'll look at median first. The median is the middle data point when you have them all in order. Now, it's not going to make a difference if they're ordered going up or ordered going down. They just need to be ordered. The middle number is going to be the same either way. Now, that definition assumes that we have an odd number of data points. If we have an even number of data points, then it's going to be the mean of the two that are in the middle. And so you'll see that we've got two different definitions here. We've got here if we have an odd number of points, and then this definition if we have an even number of points. So that's why when you see this definition, there's two different ways of thinking about it, the odd number definition and the even number definition. Some books will say it's the middle data point in a list of an odd number of ordered data points, or the mean is the mean of the middle two in a list of an even number of data points. Some definitions will be specific with it. But I'm just giving you this definition because the first part doesn't make sense if there's an even number, and the second part doesn't make sense if there's an odd number. So it sort of implied what's going on here. So same thing. Let's find the median of this set. So let's count. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9. So we've got 9 numbers, and so the middle is going to be the fifth one. So we could see 1, 2, 3, 4, 5. In this case, the median is this 7. Another way of doing this, if figuring out what the middle number is going to be, might be kind of complicated for some students, would be just to start marking off. Let's take off the smallest one and the biggest one. Let's take off the smallest one and the biggest one. Smallest, biggest, smallest, biggest. And then look at what's left. If there's only one number left, then we know there was an odd number of things, and that's going to be our median. If there was an even number, then we would have two numbers in the middle, and we would know to take the mean of those two numbers that are left. Or maybe there's no numbers left, and you shouldn't have crossed out those last two. But if this odd and even conversation is going to be a little bit too much of a challenge for some students, and the odd and even conversation is starting to get in the way of the median conversation, then we can sort of go around all that and just start marking off the biggest and smallest, and then the biggest and smallest of what's left, the biggest and smallest of what's left, and keep going until you get down to that number. But this is going to be my median. It's the one that's in the middle. As it turns out, the median and the mean are the same for this data set, and there's nothing wrong with that. That certainly happens. But this would be the median for this data set. So when should we use either the mean or the median? In the previous example, we saw that they were both 7, so in that case, it wouldn't make a difference. But let's look at this data set, which is the same data set that we used before, but I've added an element. I've added 937. Now, we know that the sum from here to here is 63. So the sum of this new data set is going to be 63 plus 937, which makes 1,000. Got some nice round numbers for these examples. And our old data set had 9 elements, and so now this is my 10th element. So this mean is going to be a little bit easier to calculate because we know a lot of the information already. So my mean is going to be 63 plus 937. And then the size is going to be the 9 plus this 937. So I'm going to get 1,000 over 10, and that equals 100. Now, if you think about what we talked about in terms of the balance beam idea, before I had these little wooden blocks on my yardstick and they were at 1, 4, 5, 5, so on, so on, so on, and the balance point was at 7. But now we've put a block way down on the end at 937. And so my balance point has now moved way down here at 100. And this is really hard to understand what's going on because the 100 isn't part of the data set. And this can be really confusing for kiddos because they see these numbers, and because they're written one after the other, it's easy to lose a sense of scale. That 1 is written right next to the 4, and that 11 is written right next to that 937. So sometimes in student minds, that 1 and the 4 are adjacent, and that 11 and 937 are adjacent, or that they're the same distance apart, when clearly they're not. 1 and 4 are 3 away, 11 and 937 are 926 away, so they're much further apart. So a number line for this is going to be kind of hard for some students to visualize, but we can certainly draw it out. But we can see that the balance point has moved from 7 all the way up to 100. Now, let's do the median of this, and I'll do the median in blue so we can kind of make a distinction here. So I'll circle mean in black, and I'll circle median in blue so we can tell which work is which. So now my median, again, we'll go through, we'll cross off biggest, smallest. The biggest and the smallest, that one, and now I got two numbers left. And so I know to take the mean of those two numbers, so 7 plus 8 divided by 2 is 15 divided by 2, or 7.5. And that's going to be my median for this data set. This is a really important point about the distinction between means and medians. When you put in an extremely large or extremely small value, what we call an outlier to a data set, it pulls the mean an awful lot. It will move the mean. The mean is very sensitive to really big and really small values. The median clearly isn't. Our mean moved up by 93. Our median moved up by a half. And so when we look at the next set of videos, we'll talk about some ideas in terms of different distributions where the mean and the median, one might have an advantage over the other. But for right now, just notice what's happening here when we put this really big value of 937 in, and how the mean is easier to move by these big values than the median. The last idea is to talk about the mode. And the mode is the data point which has the highest frequency. It's just the thing that happens the most. Now, if we have categorical data, and everything we've been talking about so far has been numerical data, but if we have categorical data, we can have a mode. We just call it the modal category. I want to point out that we can't really do mean and median with categorical data because it doesn't make any sense. I can't add red plus blue and divide it by 2. That doesn't really mean much of anything. So for categorical data, mean and median don't mean anything. But mode does, but we call it something different because it's not a mode number, it's a modal category in that case. So this first one is for numerical data, and this second one is for categorical data. So now let's find the median of, the mode of this data set. So if we look at which one occurs the most, and if we were to go back and look at that dot plot, we'd be able to tell because it would be the number that had the most dots over it, and we can see that it would be 11. So 11 is going to be the mode for this data set. That's it. I'm not going to lie, mode doesn't get used an awful lot in like actual statistical work. It's a good thing to notice. There are some ideas that use mode that we'll actually talk about in the next video. But as far as like serious statistical work does, mode isn't something that gets used an awful lot. So here's your checkpoint question. Alice has 3 candies and Bob has 2 candies. So you can see the average there would be 2.5 candies. Now, when Charlie joins them, they find that the 3 of them have an average of 4 candies. So how many candies must Charlie have? So this is a common question that you'll see in a lot of books dealing with statistics and mean and arithmetic mean, because it's making you think about that approach in a slightly different way. So I want you to think about how you could solve this problem, not just computationally, but using those approaches that we talked about, the balance beam and the leveling off approach. So you could probably figure it out numerically fairly quickly, but how would you explain that and how would you model that? As always, if you have any questions about this problem or anything else from this video, please be sure to ask in class and we'll get your questions answered. All right, thank you.